Okay, I think that is going. Just in case. There was a long piece. Huh? I left my microphones, so just relying on the phone. Probably need to remember to talk a little louder, but my throat's a little more tired. So might be a little bit more quiet of a lecture. All right, quick recap. Starting with open sets or a topology. Topology, collection of open sets, same thing. So topology, a topology tau on X satisfies three properties. First off, the empty set is in tau, or in other words, the empty set is open, and then the entire set X is open. That's property one. Property two is if you have any finite collection of open sets, n of them, then the intersection of those n sets is also open. So an intersection of finitely many open sets is still open. And then finally, if you have any arbitrary collection of open sets, its union is open. Any arbitrary collection of open sets is open. Now, closed sets had almost identical properties to open sets. Their properties are what happens if you just take the complement of everything. Since X is open, the empty set is closed. And since the empty set is open, X is closed. Remember, what's the definition of a closed set?
The complement of an open set.
It's the complement of an open set. So if a set's complement is open, it's closed. Now, remember that when we take complements, then when we take complements, it turns unions into intersections, and it turns intersections into unions. This ultimately came from what we call De Morgan's, which is that not alpha and beta is the same thing as not alpha or not beta. So not is like complement, and is like intersection, or is like union. So if you have not the intersection of two sets, then you have not the first set union with not the second set. Or the complement of an intersection is equal to the union of the complements. Writing this out set theoretically, let's rewrite the exact same thing but with set theoretical notation. What are we saying? We're saying alpha intersected with beta complement is equal to alpha complement union B complement. Sorry, I said alpha and beta, I meant A and B. Same principle. So if you complement this, you get this. So here we have a finite number of open sets. Here we have a finite number of closed sets. If the intersection of finitely many open sets is open, then the union of finitely many closed sets is closed. Similarly, here we said an arbitrary union of open sets is open, therefore an arbitrary intersection of closed sets is closed. Just comes from the complement. Okay, so now today we're going to move on to the notion of the interior of a set and the closure of a set. Now yesterday in geometry, I went over interior and exterior, and so don't let me accidentally say exterior when I mean closure. I should never be saying exterior today. I might accidentally say it because of my lecture yesterday. Don't let me do that. We're talking about interior and closure. Okay, let's get intuition for what these things are. So imagine I have this set A. We're going to be looking at the standard topology in R2. Let's remind ourselves what's the standard topology in R2. R2 is the plane. So what are our open sets in R2?
The empty set.
The empty set is open. The entire, all of R2 is open. But what was our basis? What were we using to build our open sets? In R2, is this set open or closed? Everything inside of here, not including the border. That's open. What about this square? Including the sets inside. That one's not open, it's closed. Okay, so what were our open sets? Remember, the shapes we make with dotted lines, any shape we make with dotted lines, or any union of shapes that we make with dotted lines, right?
Yeah.
Now, any shape we can make with dotted lines, we can make out of a union of open balls. Right?
Yes.
To get this shape here, whatever our weird shape is that we have, sorry, didn't mean to include that, just not good dotting. Whatever weird shape we have, if you let me use infinite precision with a bunch of little open balls, I could union up enough little open balls to reconstruct that shape. So, the standard topology on R2 is any set you can create by unioning together open balls. And then the empty set. And obviously you can get all of R2 by unioning together open balls. Okay, so this was an open set. You've already got good intuition for it. That was open set, the square was closed. Look at A here. So A, we're including the boundary over here. We're not including the boundary here, and we're including all the points inside. Is A open?
No.
No. How do you know it's not open?
Because you can't get exactly on that solid line.
Right, this part of the solid line, pick a point right there on that solid line. There is no open ball you can create which gives you that point, which doesn't also get some points outside the line. If I tried to create an open ball around that point, no matter how small, I'm always going to include at points outside the circle. So I cannot reconstruct the circle with some of its boundary points, these boundary points here, with just open balls. Sorry, probably can't see that very well. I was saying this side colored in, including the boundary over here, and then not that boundary. So, is it open?
No.
Is it closed?
Yeah.
It's closed?
Yes.
No, because of the other side.
No, let's look at the complement of it. What would the complement of this thing look like? So, this doesn't have these points, so the complement would. It has these points, so the complement wouldn't. And then it would be all the points outside, right? Here's the complement of this set. Is this set open? No, same problem with these boundary points. There's no way I can create an open ball around one of those boundary points and not get some of these points I'm not supposed to get. So this is not open, so this can't be closed. Look at its complement. Its complement is open. Now its complement's not open.
Yeah, it's complicated.
So this isn't closed because its complement is not open. So this set A over here, it's not open and it's not closed. With me? Takes a lot to get your intuition developed for this. Topology is a very unintuitive field. So here's A, it's not open, it's not closed. Right? Now, describe for me what would be the biggest open set we could create inside of A.
Just
Everything up to the.
everything up to the border. So
Yeah, just get rid of these boundary points.
Yeah, no.
So it would basically be something that looked like this. All the points inside, not including any of the boundary points. That's the biggest open set we could fit inside of there. You with me?
Yeah.
Now, what is the smallest closed set we can create containing it?
Same thing, but the complement of the other set.
I think you have the right idea, but what you said isn't quite right.
It's you can't get you can get
The
infinite
smallest
small.
closed set that contains this whole thing.
Would be the point for the boundary.
Same thing.
Just include the boundary points. The same thing, but just include the boundary points. That's the smallest closed set that contains the whole thing. So, there's the smallest closed set that contains the whole thing. If we did the dotted line, then that's the biggest open set we can create that's contained in it. That is going to be what we mean by the interior and the closure. The interior of a set is going to be the largest open set we can create inside of it. And the closure of a set is going to be the smallest closed set we can construct containing it. So the closure of A is going to be this set, and the interior of A would have been that set if we didn't include the boundary. So if that would have been a dotted line around.
So what do you call something that isn't open or closed?
A here is a set that is not open or closed.
Right.
But for any set A you choose, as long as, even if it's empty, pick any set A you want. I can always find an open set that's a subset of it. Worst case scenario, I pick the empty set. So, no matter what set A you choose, I can always find the biggest open set it contains. So A here is neither open nor closed. But we found the biggest open set it contains, and we also found the smallest closed set that contains it. Right?
Yeah.
You can do that for any set A. Any set A you give me, I can find both its interior and its closure. So every set in topology has those two associated sets. And you'll notice a nice property is that the smallest open set inside of A interior, we use this notation for it, is always going to be a subset of A, is always going to be a subset of the closure of A. And we're going to have those three properties. The smallest closed set containing A always has all of A, and A always has all of the largest open set inside of A. Now we're going to define these two a little bit different, but I think you've got the intuition for what they are. Because smallest closed set containing A, that's not a very good mathematical description. And largest open set contained in A, that's not a very good mathematical description either. So now we're going to come up with precise definitions for those exact things. Okay, so interior and closure, here's our definition. Let A be any subset of X, like this, where X is X tiles the topological space. Okay, the interior of A, which is denoted by either int A or A with that circle above it, typically we'll use A with the circle above it. Occasionally we use this notation because the circle above it can be confusing. So the interior of A, denoted this way, is the union of all open sets contained in A. Pick an open set that's a subset of A. Pick another open set that's a subset of A. Take all the open sets that are subsets of A and union them all together. That gives you your interior. That's the biggest open set you can fit in A. Take all the open sets you can fit in A, union them all together. That's the biggest possible one you can get in A. Make sense? That's interior. The closure. Very similar. The closure of A, which we denote as CLA or A with a line above it, typically we'll use this notation, is the intersection of all closed sets containing A. So look at every closed set that has A contained in it and intersect them together. Every time you get the intersection of two sets, you're making it smaller, right? So we take every possible closed set we can think of that contains A and intersect them all together. Their intersection is still going to be a closed set because an intersection on any number of closed sets is still closed. So the intersection of all those closed sets is still closed, and it's going to contain A because we intersected together a bunch of sets that contain A. So those are their precise mathematical definitions. Make sense? Okay. Example. Here's a slightly more complex set. A has these boundary points, doesn't have these boundary points, then has this weird handle piece sticking off, including that line segment. That's just a line segment. You with me? Now, the largest open set contained in A is just get rid of all the boundary points. Those are all boundary points, that's a boundary point, so you're left with just that. Right? The closure on A, the smallest closed set containing A, is basically going to be what you get if you include all those boundary points. There it is. I didn't mean to make those circles get bigger. Those were all meant to be the same size. Make sense? Yeah. Okay. Let's prove some theorems. Not sure how far over I can go. Yes, I can go to that one. Okay. So let's prove a theorem. So let A be a subset of X, B be a subset of X in the topological space X tap. So we got our topological space. A is a subset of X, B is a subset of X. Two random subsets. If U as a subset of A is open, then U is in the closure of A. So if U is an open set inside of A, then U is an open set in the interior of A. Did I say closure? Interior. Sorry. If U is an open set in A, then U is in the interior of A. Come back to this picture here. Draw any open set inside this set A right here. Whatever open set you try to draw inside of A, as long as it's completely inside of A and it's an open set, that same set is also going to be inside of A's interior. Right? So, if U is a subset of A and it's open, then U is in the interior of A. And another way that's obvious is by definition, A interior is the union of all open sets contained in A. U is an open set contained in A interior is the union of all open sets contained in A. So U is one of the sets you union up to get A interior. Okay, similarly, if A is a subset of C, so notice up here that the open set was inside of A. This time we're going to have A is inside of a closed set. So, if A is a subset of C, where C is closed, then the closure of A is a subset of C. So this is going the other direction. This is saying pick any closed set you want that contains all of A. Here's a closed set that contains all of A. Right? That same closed set is going to contain all of A's closure. If I took that and redrew it around there, it would still contain it all. There's no way for me to draw a closed set that contains all of A, even if I came in here and got right on the boundary, and then popped back out like that. We still are going to include all of A's closure. There's no closed set I can draw around A that doesn't include all of A's closure. So here's a potential C. So the point is, A's closure is always a subset of C if A was a subset of C, where C is a closed set. So any closed set I can create around A, it's going to contain A's closure. So if A is a subset of C, where C is closed, then A's closure is a subset of C. Okay, next one. If A is a subset of B, then the interior of A is a subset of the interior B. That one I think is pretty intuitive. If all of A is inside of a set B, then all of A's interior is inside of B's interior. Okay? Similarly, if A is a subset of B, then all of A's closure is inside of all of B's closure. If we include the boundary points of this set and this set, then the subsets are still going to be true. If this is a subset of this, then when we include the boundary points, we didn't change anything. They're still subsets of each other. Make sense? Yeah. And then finally, these two. A is open if and only if it's equal to its own closure, or its own interior. And A is closed if and only if it's equal to its own closure. So those are what we're proving. Let's go through each proof. Each of them are pretty small proofs. So starting with number 1 here. Proof. If U is a subset of A and U is open, then U is a subset of the interior of A. So let's prove it. Let U be a subset of A where U is open. Then U is an open subset of A. What is A interior? It's the union of all open subsets of A. So U has to be a subset of A's interior, by definition of A's interior. Close set, almost identical thinking. If A is a subset of C where C is closed, then A's closure is a subset of C. So let A be a subset of C where C is closed, then C is a closed set containing A. What is A closure? It's the intersection of every closed set containing A. So A closure is contained in every closed set that contains A. A closure is the smallest closed set that contains A. Any bigger closed set that contains A definitely has A closure. So by definition of A closure, it's a subset of any closed set containing A. Alright. Slightly more, well, I don't know, I'd say more interesting. Okay. If A is a subset of B, then the interior of A is a subset of the interior of B. That's what we're proving now. So let A be a subset of B, and observe that the interior of A is always a subset of A. Right? By definition, the interior of A is always a subset of A. But I know that A is a subset of B. So the interior of A is a subset of B. So the interior of A is an open set. The interior is always open, the closure is always closed. So the interior is an open set, and it's inside of B. What is the closure of B? Or sorry, what is the interior of B?
A is subset of the interior of B.
A is a subset of B, maybe not a subset of the interior B. Should we draw a picture of that real quick? So I'll draw A as a subset of B where A is not a subset of the interior B. So let's see, how am I going to do this? I want A is a subset of B, but A is not a subset of the interior of B. Okay, so here's B, and then A comes and it includes boundary points right there, and then not there. Okay, here's A. So A is a subset of B, right? But notice that A includes these boundary points. If I took the interior of B, B interior, then that would look like this. And yet A would include those boundary points. So A is a subset of B, but A is not a subset of the interior of B. However, the interior of A, if we draw A's interior here, so it's a dotted line like that, it is going to be a subset of the interior B. Now, how do I know that? I know that A interior is an open set, and I know that A interior is in B. By definition, B interior is the union of all open sets in B. A interior is an open set in B. B interior is a union of all open sets in B. Therefore, B interior is the union of A interior with other open sets. So it for sure has A interior. That's one of the sets you union together to get B interior. If we union every single open set inside of B, one of the open sets we union together is A's interior. That is one of the open sets inside of B. B interior is a union of all possible open sets inside of B. Every single one. All infinitely many. It's okay that we do all infinitely many because we know that a union of infinitely many sets is still open. So B interior is still open. That makes sense? New notation, always a pain in the butt the first time you come across it. It just is dense. So even though these are simple proofs, you're probably going to have to stop and rethink the same thoughts over and over again until they sink in. So keep thinking about it. Don't give up on me. All right. So we just did this one, right? Yeah, is that the one we just did? The interior of A is always a subset of the interior of B. If A is a subset of B, yes. Okay. Now if A is a subset of B, then what was A with the line above it? A closure is a subset of B closure. Okay, let's prove that one. Let's remind ourselves, what is A closure? Intuitively, it's the smallest closed set you can create that still contains A. We're trying to squish A into the smallest closed set we can possibly fit around it. Very tight-fitting closed set. So if A is a subset of B, then the closure of A is a subset of the closure of B. That's what we're going to prove. Now, the closure of a set is always open or closed?
Closed.
Closed. The closure is always closed. The interior is always open. Okay, so always remember that those are closed sets. Okay, so let's prove this. Let A be a subset of B, and observe that A is a subset of B, and B is always a subset of its closure. B closure is the smallest closed set containing all of B. So B closure always has all of B, right? And A is a subset of B, therefore A is a subset of B closure. So everything in A is in B closure. Okay, here's a tricky bit of thinking. That means that B closure is a closed set that contains A. A closure is the smallest closed set that contains A. B closure is a closed set that contains A. So B closure has to contain A closure. Or, to say that more mathematically, A closure is the intersection of every closed set containing A. B closure is a closed set containing A. So B closure is one of the sets we intersected together to get A closure. A closure is the intersection of every closed set that contains A. If it's the intersection of all those sets, it is the things that are in all of those sets. That's what it means when I intersect a bunch of sets together. If I intersect your math class with your science class with your humanities class, I'm saying who's in your science class and in your humanities class and in your math class. That's what the intersection is. So when you intersect those three classes together, you're saying who's in all three of those. So when I do the intersection of every single closed set containing A, then we get the set that's in every single closed set containing A. So B closure is a closed set containing A. A closure is the intersection of every closed set containing A. Therefore, A closure is a subset of B closure. So B closure is a closed set containing A. Therefore, A closure is a subset of B closure. A closure is a subset of any closed set containing A. B closure is one of those. Overstating it? You got it? Okay. Next one. A is an open set if and only if it's equal to its own interior. What is the interior of this set? It's the whole set. What's the biggest open set I can fit inside of there? The whole set, because the whole set's open. That's what we're saying. So a set is open if and only if it is its own interior. Okay. So A is open if and only if A is equal to its interior. So first off, let's prove this direction. This is an if and only if. We need to show that if this is true, then this is true. And then we need to show that if this is true, then this is true. So first I'm going to show that arrow is saying we're going to do this way first. I'm going to show that this implies this. So assume A is open. So let A be open and observe that A's interior is always a subset of A. Maybe we should write that somewhere. Something that we always and forever know. That A's interior is a subset of A is a subset of A's closure. This is always and forever the case. So let A be an open set and observe that A's closure is a subset of A. By definition. I'm trying to show that if A is open, then these two sets are equal. How do I show that two sets are equal? How do I show two sets are equal? Let me move the camera so I can start drawing on the whiteboard. Ooh. See the, yeah. Okay. Are those two sets equal?
No.
No?
Yeah.
Yes. Remember, duplicates don't matter in sets and order doesn't matter in sets. Right? So this is the set 1, 2, 3, this is the set 1, 2, 3. Right? How do we know that those sets are equal?
Because they have the same values.
Because they have the same elements in them. I know everything that's in here is in here, and I know everything that's in here is in here. Right? That's the two things you check. If I were to suddenly put a 4 here, you would know that these sets are not equal. Right? Everything that's in here is in here, but there are some things in here that are not in here. So, if we go back to our definition of set equality, set A is equal to set B if and only if A is a subset of B and B is a subset of A. So that's how you prove two sets are equal to each other. You prove that they're subsets of each other. Everything that's in here is in here and everything that's in here is in here. That's how we prove it. You with me? So, here I am. I know A is open. I'm trying to show that A is a subset of A interior and A interior is a subset of A. Well, we get, so let A be open and observe that A interior is a subset of A by definition of the interior. So we got half of it already done for us. Now I just need to show that A is a subset of A interior. Because I'm trying to show that they're equal. So I already showed this one's a subset of this one. Now I need to show this one's a subset of this one. right? Now remember, what is A interior? It's the union of all open sets contained in A. Since A is a subset of A, then A is an open subset of A. A is an open set contained in A. A contains itself. So therefore, A is in the interior. What's the interior? It's every open set contained in A. A is an open set, and A is contained in A. So A is in the interior of A. So I got A interior is a subset of A, and I got A is a subset of A interior. Therefore, they're equal. Okay, we proved the forward direction. I just already showed that if A is open, then A is equal to A interior. Now I need to prove the other way. I need to show that if A is equal to A interior, then A is open. But A interior is always an open set. So if A is equal to A interior, is A open? A interior is always an open set. A is equal to an open set. Is A equal? Or is A open?
Yes.
Yes. Okay, so that's all we say here. Now let A equal to A interior. And A is open, because it's equal to an interior, which is an open set. There we go. I showed if this is the case, then this is the case. And I showed that if this is the case, then this is the case. So they're logically equivalent statements. It says the same thing. If you say a set is open, that's logically equivalent to saying that set is equal to its interior. Okay. Next one. Similar idea, but now with closures. A is closed if and only if it's equal to its own closure. Once again, if and only if. So I need to show this being true implies this is true, and then this being true implies this is true. Let me go this direction first. That's what that arrow is showing the reader. Let me show this implies this. So let A be closed. And observe that A is always a subset of its closure. That's always the case. Then, since A is a subset of A, well, let's think about what's A's closure again.
The smallest
It's the
closed set.
smallest closed set.
It's the smallest closed set containing A. If you can find any other closed set containing A, then that also has to contain A closure. Because A closure is the smallest closed set containing A. If any other closed set also contains A, it must contain A closure. Okay, so since A is a closed set containing A is a subset of A, where A is a closed set. So A is a closed set containing A. So since A is a subset of A, sorry. That's nothing. Since A is a subset of A, and A is closed, comma, then A closure is a subset of A. Oh, maybe I finished it here. Maybe why I erased it bad. Since A is a subset of A and A is closed, comma, then A is a closed set. Since A is a subset containing A, comma, then A is a closed set containing A, which gives me that A closure is a subset of A. Okay, I think that's why I had it there before and I erased it. Let's say that one more time to make sure we didn't get confused. So I'm trying to show that A closure now is a subset of A if A is closed. A closure is the smallest closed set containing A. Any closed set that contains A has to also contain A closure. A is a closed set containing A. So A has to contain A closure. That's what we're saying here. So since A is a closed set containing A, since A contains A, then A is a closed set containing A, which means that since A is a subset of A must be equal to A closure. Which gives us that A closure is a subset of A, therefore the two sets are equal. So I showed one's a subset of the other is a subset of the one, therefore they're equal. Good? Alright. Now the other direction. The other direction is real easy. A closure is always open or closed?
Close.
Closed. A closure is always closed. So if A is equal to A closure, then A is closed. So now, let A equal A closure. Then A is closed, because it's equal to a closure. Alright. Now, let's do some examples with some topologies, finding the interior and the closure of the different sets. So, we're going to jump now to the standard topology on the real numbers. What's the standard topology on the real numbers? So, real number line, what are our open sets?
R1.
From
We're on
zero
R1, that's what we mean by the real numbers.
to negative,
So the whole set R is open and the empty set's open. Okay, we got that.
negative infinity, positive infinity.
That's all of R. That's one.
That would be your power set. Or your power.
No,
Power set is topology, isn't it?
the power set is all possible subsets. You're just taking the whole set R. Negative infinity to infinity, that's what we mean by R. All the numbers from negative infinity to positive infinity.
Yes.
So we're talking about the standard topology on R. What do our open sets look like? Is all the points from 1 to 3, including 1 and 3, open?
No.
No. What if we didn't include 1 and 3?
Then it's open.
So we did it like this. Now is it open?
Yeah.
Yes. We call that an open interval. What were our open sets on R? Open intervals and any union of open intervals.
Yeah.
It's like the one-dimensional version of open balls. Imagine that I have an open ball and I intersect that with the one-dimensional universe, i.e. a line. What am I left with?
Everything that.
I'm left with the open interval from here to here, not including those endpoints. Or imagine I had a three-dimensional open ball. So a ball, all the points inside of it, but the skin's missing, right? And I intersect that with the whiteboard. What am I left with? I'm left with this right here. So it's the same shape, just in different dimensions. So the standard topology on R is still just unions of open balls. It's just one-dimensional open balls or open intervals. Okay. So, question. Is the set containing 1 open? Just that point. Drawing it on the number line, there's 0, there's 1, there's 2. We just have this point. Is that an open set?
No, because you always get a little bit lower. A little bit.
Yeah, any little tiny open interval I create around 1, any open interval I come up with that contains 1, is also going to contain infinitely many points to the left of 1, and infinitely many points to the right of 1. The only finite set in the standard topology on R, the only finite open set, is the empty set. Every other open set has to have infinite elements in it. Okay? Let's go the other way. What about the set containing 1? Is it closed?
No, because it's close.
What's its complement? Its complement is everything except 1, right? So that's all the numbers from negative infinity to 1, not including 1, union together with all the numbers from 1 to infinity.
Oh, yeah.
Open interval, union of open intervals, we're good. So this is a closed set because this is an open set. Standard topology on R. Okay. Now let's look at the sets I gave you here. So A, first we'll look at this one. A is equal to the interval from 0 to 1, including 0, not including 1. That's it. Is it open? No, because there's no way to get the point 0. Is it closed?
No, because the opposite of the.
No, because its closure, or not its closure, because its complement is going to have the interval from 1 to infinity. So if we take the complement of that, what do we get? We get negative infinity to 0, not including 0, union together with 1 to infinity, including 1. So it's not open, it's not closed.
Okay.
Intuitively, you have an intuition for this. Open sets, when we're talking about one of the standard topologies, open sets don't have all their boundary points, closed sets do have all their boundary points. This is missing a boundary point, so it can't be closed. and it has a boundary point, so it can't be open. Right? It's the same intuition you have when I draw these pictures over here. It's just a one-dimensional version of that intuition.
So do you label it open and closed, or neither?
That is neither open nor closed. There are sets that are open and closed. The empty set.
X set and X.
And the whole set R. X in general, but in this case R. Because our X is R in this case. Okay. So now, what is the interior of A? What is the smallest, or sorry, what is the largest open set you can create inside of A?
X being not including 0 and not including 1.
The open interval 0 to 1. That's what it is. What's the closure on A?
The closed interval including 1.
The closure interval from 0 to 1.
Yeah.
Wonderful. Alright, now let's move on to the rationals. We remember what the rationals are? All possible fractions. To be more explicit, it's all the numbers a over b, where a and b are integers, and b is not equal to 0. So take any two integers, put them over each other, as long as b is not 0, that's how we get a rational number. Right? Okay, so we're looking at the rationals. What is the interior on the rationals? What's the biggest open set you can create inside the rationals?
The empty set and rationals.
The empty set and the rationals?
So the biggest open set in rationals?
The biggest open set we can create inside the rationals.
You can't create one, can you?
It would be the open, it would be the empty set.
The empty set.
Just the empty set.
Just the empty set. Nothing else. There's no points I can include in R, in Q. There is no open interval I can fit inside the rationals. Any open interval, no matter how you create it, is going to have some rationals, but it's also going to have some irrationals. You can't create one that just has rationals. If we're looking on the number line, there is no interval I can create that doesn't have irrational numbers. It will always have some rationals. We'll have rationals in there. But we'll also always have some irrationals in there as well. We'll have infinitely many of both. So, the interior of the rationals is just the empty set. What's the closure?
The empty set.
The smallest closed set that contains all of Q. Does the empty set contain all the rationals?
Oh no.
So that can't be it. We need the smallest closed set we can come up with that has every single rational in it. Smallest closed set I can come up with that has every rational number.
Is it just maybe rational numbers?
Are the rationals closed? Let's look at the complement of the rationals, which are the irrationals. Are the irrationals open? No. Any open interval I construct is going to have both rationals and irrationals. I can't create the irrationals with just open intervals. Any open interval has both rationals and irrationals. So I can't get just the rationals with open intervals, and I can't get just the irrationals with open intervals. So the rationals are not open and they're not closed. So it's definitely not the rationals, because the rationals aren't a closed set. So what's the smallest closed set that contains all the rationals?
Is there one?
There's always one. Every set always has an interior, and it always has a closure.
The power set?
The power set is a set of all possible subsets. That's not,
An option.
yeah.
Would it be the real number?
It's just the real numbers. It's the whole set R. The whole set. That's the smallest set that contains all of them. The whole thing. If you try to include any little piece of R, any little interval of R, then you're going to miss some of the rationals. There's no closed interval we can get rid of. Okay. So that was a good one for our intuition. Let's move on to this one. Now we're on the lower limit topology on R. So rather than our open sets being made with open intervals, our open sets are made with intervals that are closed on one side and open on the other. So this is an open set in the lower limit topology. Really quick, let's look at the complement of that thing. What's the complement of that thing? It's all the numbers from negative infinity to 0, not including 0, union together with all the numbers from 1 including 1 to infinity. Right? Notice that I can create this from unioning a bunch of things that look like this together. Right? So this set A is both open and closed in the lower limit topology. Right? Okay, so now what is the interior of A?
It would be A.
The
A? A is open if and only if it's equal to its own interior.
Yeah, but
Is A open?
Yeah.
Oh, sorry, on this one. Is it open?
no, it's open and closed.
So is it open?
Yes.
What?
Open and closed are two separate properties. You ask, are you open? Yes or no. Are you closed? Yes or no. Just because you're open, you being open has nothing to do with you being closed, and you being closed has nothing to do with you being open.
Okay.
Right?
Yeah.
So, is this set open? Up here. Is it open? On the lower limit topology?
Yeah.
Yes. And the set is open if and only if it's equal to its interior. So it is its own interior. What's the closure of the set?
A.
The closure of the set is also A, because A is a closed set. And the set is closed if and only if it's equal to its own closure. Okay. Now we're going to move to the finite complement topology on R. Uh-oh, this is a hard one. Finite complement topology. The set is open if and only if its complement is finite. Let's look at the set A. Is this an open set? Well, let's look at its complement. What's the complement of this set? It's all the numbers from negative infinity to 0, not including 0, union together with all the numbers from 1 to infinity. Question, how many points are in this set when we union all those together?
Infinite.
So is it finite?
No.
No. So this set does not have a finite complement. So it is not open in the finite complement topology. Let's try another one. Let's say my set U is equal to all the numbers from negative infinity to 1, union together with all the numbers from 2 to infinity. So we're only missing the numbers between 0 or between 1 and 2, right?
Yeah.
Is this open in the finite complement topology?
No.
No?
Yes.
What's the complement of this set?
Everything that's in between 1 and 2, which is an infinite.
Everything between 1 and 2, including 1 and 2. How many things are in that set?
An infinite.
An infinite number. So this is not open, because its complement is not finite. What about if we did negative infinity to 1, union 1 to infinity?
And yes.
Then yes, it is open. How do I know it's open? What's its complement?
1.
The set containing 1. How many things are in there? 1. That's finite. We finally got a finite one. So that's what our open sets are. They're sets with a finite complement. Okay, so now, on the finite complement topology, what is the interior of the set? thinking. As long as you need.
Okay.
The interior of that set. What is the biggest open set we can create inside of there?
The interval
0 not including 1.
0, not including 0 to 1, not including 1.
We are on the finite complement topology. So open sets have to have a finite complement.
Oh.
How big is a complement of the sink?
Infinite.
Infinite. So if I take a subset of the sink, what's its complement going to be? Infinite.
Still infinite.
If this sink's complement is infinite, then anything smaller than that still has an infinite complement. If I make a set smaller, I make its complement bigger. If I take a subset of this sink, then its complement just gets bigger and bigger and bigger. So this already has an infinite complement. There's no subset I can take of this sink such that its complement is magically now finite. So what is the smallest, or what's the biggest open set I can create? There is one. That, I think you have the right idea. The empty set.
Oh.
Yeah, that's what I meant.
Yeah. The empty set. That's the small, or that's the biggest open set you can fit in there.
Is the empty set equal to nothing? So it just means nothing?
No.
Okay.
Let me show you what nothing looks like. Right here, I'm going to draw it for you. Want me to draw it again?
No.
Here we go a third time.
Yeah.
There's nothing. Let me draw the empty set now. What's nothing? It's what rocks dream about. Rocks don't dream about the empty set. There's a big difference between nothing and the empty set. Right?
Yeah.
No, it's good. It's hard to get good intuition for nothing. Watched an interview with a blind guy. He was a guy who had his sight and then he lost it in life. And so one of the questions was something to the effect of, what was the most surprising thing about going blind? He says, I want you to know, I don't see black. You know, you watch the movies, I always thought if I lost my sight, suddenly I'd see black. It's not that I see black, it's that I don't see. I now see out of my eyes what I used to see out the back of my head. I don't. So I don't see black, I see nothing. I don't see. Good intuition for nothing. So the empty set is not nothing. It's very different from nothing. Okay. Oh, I lied to you. Because now what's the closure of this set? What's the smallest closed set containing the set?
It should just be A, right? Because that's
Is A closed?
yeah, because the complement is
So a set is open if it has a finite complement.
and this
Which
was
means-
answered, yeah.
A set is open only if its complement is finite. So only finite sets are closed. Right? A set, what does it mean for a set to be closed? It means its complement is open.
Yeah.
Now in the finite complement topology, a set is open only if its complement is finite. So the complement of open sets is finite sets, and the complement of open sets is closed sets. So closed sets are finite sets. Good? Okay. So, if our only closed sets are finite sets, what is the smallest closed set containing this? How many things are in here?
Infinite.
Infinitely many. I can't create a finite set that contains this. So is there a closed set that contains it?
No.
R, the one exception. Is the empty set open? Always. So R is closed. So two sets always and forever are both open and closed. The empty set and the entire set X. The empty set and the entire set X. They're always both open, they're always both closed. So there always is an interior, and there always is a closure. Worst case scenario, your interior is the empty set, and worst case scenario, your closure is the entire set X. Right? Okay. Now the one that you guys are always rushing to get to. Let's look at the power set on R. So we have R together with its topology is going to be the power set on R. Every possible subset of R. Right? What sets are open? Any possible subset of R you can come up with. That's what's open. Every possible set you can think of is open. Which sets are closed?
Everything you can't think of.
Empty set.
The empty set.
If anything is open, then anything is closed. Take any set and look at its complement. Is it open? Think of any set. Doesn't matter which set. Take its complement. Is its complement open? Yes, because everything's open. So if everything's open, everything's closed. So A here, let's look at A. Is it open?
We're not going off.
We are in the power set on R. What are open sets? Every possible subset of R. Is that a subset of R?
Yes.
Yeah, so it's open. Our open sets, our topology, is the power set on R, which is a set of all possible subsets of R. Every single one. Here's a possible subset of R, so it's in there. Right? Let's look at its complement. Its complement is all the numbers from negative infinity to 0, not including 0, union together with all the numbers from 1 to infinity. Is this a subset of R? So it's open. So then that's closed. So this is both open and closed. And this is both open and closed. Yeah, we call them clopen. Every single subset of R is clopen when we're talking about the discrete topology, or the power set topology. Right? Yeah. So, what's the interior of A? Up here we said A interior is the empty set. We said A closure. So R. Okay. Down here, what's the interior of A? What's the biggest open set you can fit inside of A?
A.
The whole set A, because A is open.
Oh, yeah.
What's the smallest closed set you can create containing A?
A.
A, because A is closed. Lots of stretching your intuition. Okay. Good examples. One thing I was going to note, so going back to our standard topology on R, and when we were thinking about the rationals, notice that the interior of the rationals was the empty set, right? Standard topology on R. Anytime the smallest open interval we can fit inside of the rationals is the empty open interval. Nothing. And then the closure on the rationals was all the real numbers. The same thing is true also for the irrational numbers. So what's true for the rationals in this case is also true for the irrationals in this case. You with me? So the closure of the rationals is all of R, and the closure of the irrationals is all of R. Okay, so definition. A subset A of a topological space X is dense if and only if its closure is the entire set. So the rationals are dense in the real numbers when we're talking about the standard topology on R. Intuitively, what does it mean for them to be dense? It means there's no section of the real number line we can cut off without getting some of them. They're dense, they're everywhere. That's intuitively what we mean by dense. Here's our actual mathematical definition. If you take a calculus course, you'll have a definition, well, maybe not calculus, real analysis, which is like proving calculus. If you ever take that course, you're going to come across notions of proof that the rationals are dense in the real numbers. And it's going to be essentially the same proof. The same thinking, I should say. So a subset A of a topological space X is dense if and only if its closure is the entire set. That's what it means for a set to be dense. It's dense if its closure is the entire set X, whatever X is. That's what we mean by dense. So both the rationals and the irrationals are dense in R on the standard topology on R. All right, moving on to quick easy theorem. So let A be a subset of some topological space, call it X, and let Y be some point in X, in big X, in our topological space. Then, Y is in the interior of A, if and only if there exists some neighborhood of Y. What was a neighborhood of Y?
All the open sets containing Y?
It's just an open set containing Y. Neighborhood of Y is just an open set that has Y in it. Right? Remember our definition of a Hausdorff topology? Hausdorff topology is where anytime you have 2 points, you can house them off from each other. You can give them their own neighborhoods. Neighborhood. Open sets. Okay. So, Y is in the interior of A, if and only if there exists some open set U sub Y containing Y, or in other words, there exists a neighborhood of Y, where that neighborhood is a subset of A. Intuitively, we have a good understanding for this. Here's some set A. Here's the interior of A. How do I know when a point is in the interior of A? When I can find some open ball around that point. Some open set around that point where that open set is completely inside of A. Sorry. So come back to A. How do I know when a point is inside of A? If I can create some open set around that point containing it. I know that the boundary isn't in the interior of A because I can't create an open set around that point containing it. So how do I know if a point ends up in the interior of A? If I can create some open set around it containing the point. That's what this is saying. It's saying a point is in the interior of A if and only if you can find some open set containing the point where the open set is also a subset of A. That's all it's saying. So let's prove it in the forward direction first. Let Y be any point in the interior of A, and observe that the interior of A is always and forever a subset of A. Right? What are we trying to do? I'm trying to show that if Y is in the interior of A, then there is some open set containing Y that's also a subset of A. So if Y is in the interior of A, then there is some open subset, namely A interior, containing Y, where the open set is also a subset of A. So let Y be an A interior, and observe that A interior is a subset of A. Then A interior is open, and Y is an A interior is a subset of A. We found some open set containing Y that was a subset of A. Pretty easy. The other direction is more interesting. So if Y is in A's interior, obviously we can find an open set containing Y that's also in A, namely A's interior. Let's go the other direction. Let U sub Y in tau be any open set such that Y is in U sub Y, and U sub Y is a subset of A. We are trying to prove that Y is still in the interior of A. Well, then U sub Y is an open subset of A. And what is A interior? It's the union of all open subsets of A. So by definition of A interior, U sub Y is a subset of A. And so if U sub Y is a subset of A, then Y is in A's interior. Sorry, if U sub Y is a subset of A's interior, then Y is in A's interior. Y is in here, so Y has to be in here. If this is a subset of this, everything in here is in here. Y is for sure in there, so Y is for sure in there. Okay, so that was pretty easy. Now we come to the most important proof of this section. This is a proof that we will use over and over and over again throughout this class. So it's a crucial one to understand. It's the big theorem of the night. So theorem 2.5, we'll reference 2.5 a lot. Let X be a topological space, and let A be any subset of X. And let Y be any point inside of big X. That's a big X, not a small x. Then, Y is in the closure of A, if and only if every neighborhood of y intersects A. Let's get intuition for this. So, if we had A looks something like, let's do our standard example of one that's not open or closed. So there's our A, and the closure of A, we're going to draw that over here. Here's the closure of A. We're saying that a point is in the closure of A if and only if every neighborhood containing that point also intersects A. So, question. Is this point in the closure of A? Here's A closure. It's all the points, including the boundary, everything aside. Do we need to shape it in? Okay. A is all these points. And A closure is all these points.
Oh, I thought A closure was everything.
It's the smallest closed set containing all of A. Here's all of A. This is the smallest closed set that contains all of A. With me now? Okay. Question. Is this point in the closure of A? Yes. What does that mean? That means go back to A over here, find that same point. That means any open set you draw that contains that point intersects A. No matter what open set I draw that happens to contain that point, I will always get some of the points in A. You with me? Now it's obviously true for most of the points in A's closure. Obviously, any open set containing that point intersects A. How else are you going to get to that point without intersecting A? Right? The only points that is interesting is these boundary points. So now let's think about this point right here. Is that point in the closure of A? Yeah. Let's look at its corresponding point over here. Its corresponding point over here is not in A. So that point is in the closure of A, but it's not in A. Right? However, pick any open set you want containing that point. No matter how small of an open set I create around that point, I'm going to get some of the points of A.
Yeah, that's right.
So, let's read this one more time. Y is in, so this is my Y, it's that point right there. That's my point Y. Y is in A closure if and only if every neighborhood of Y intersects A at some point. So it's in the closure only if, no matter what open set I create around there, I intersect A. That's the only way it can be in the closure of A. Let's do it one more time with a point that's not in there. Let's look at a point right next to it. Is that in the closure of A? No. It's outside. Right? According to this, if we look at its corresponding point over here, so its corresponding point over here would be like that, right? If it's not in the closure of A, then that means that there's at least one open set I can draw around there so that it doesn't intersect A. And notice I can do that. I can be really careful not to go inside of A, but gather up that point. So if the point is in the closure of A, then every open set I draw around it gets part of A. If the point is not in A, then I can draw at least one open set around it and not get any of A. That's what we're going to prove. So here it is in more dense writing. Y is in the closure of A. Y is in here if and only if for every neighborhood of Y, for all use of Y now just means a neighborhood of Y, some open set containing Y. We're going to start using this notation a lot for a neighborhood. So for any neighborhood of Y, that neighborhood intersected with Y is not empty. If A is in the closure, then any neighborhood around that point, so here we're saying when it's in the closure. So go back to talk about this point. So here's our Y. It's in the closure. Here's our corresponding Y over here. Y is in the closure if and only if, for every neighborhood, its intersection with A is not empty. If I draw any open set around that Y, no matter how small, does it intersect A?
Yes.
Yes. So its intersection, whatever it is it's not empty. There is something in there. You with me? Logically equivalent, You guys aren't familiar with the contrapositive of this, but if you just take the contrapositive of this, you get this. But let me walk you through the logic of it. This says the same thing as if a point is not in the closure of A, so if we have a point out here, so now this is our y. If it's not in the closure of A, it's out here. It's not in the closure of A if and only if there is at least one neighborhood I can create around y. One neighborhood of y, here's one. If and only if there's at least one neighborhood of y, there exists a neighborhood of y, such that the intersection with A is the empty set. Make sense? So this and this both say the same thing. It's the same theorem. If you prove this, you've proven this. If you prove this, you've proven this. They're logically equivalent versions of each other. One is just contrapositive of the other, that's what we call it. Contrapositive, just so you know, if alpha implies beta, then not beta implies not alpha. That's what we mean by contrapositive. Let me give you a feel-good example with words. I tell you, it is the case that if I'm wearing shoes, then I'm wearing socks. Right? Alpha is I'm wearing shoes, beta is I'm wearing socks. That says the same thing as if I'm not wearing socks, then I'm not wearing shoes. If I'm wearing shoes and I'm wearing socks, says the exact same thing as if I'm not wearing socks, then I'm for sure not wearing shoes. You with me?
Yeah.
So that's what this is doing. This right here, we say, this is saying alpha is logically equivalent to beta. That's the same thing as alpha implies beta and beta implies alpha. So it says the same thing as not alpha is logically equivalent to not beta. Because we're doing the contrapositive of both. We're taking the contrapositive of alpha implies beta and the contrapositive of beta implies alpha. That gives us not alpha implies not beta. And so alpha implies beta and beta implies alpha is the same thing as not beta implies not alpha and not alpha implies not beta. So that's what this logic is. Okay, so there's the picture for it. There's the logic of it. There's what we're trying to prove. We're going to reference the theorem a lot. Let's try to prove the theorem. And hopefully I can do it on the fly. Okay, so it turns out this version of it is easier to prove than this version. So I'm going to prove this version of it. I'm going to show that if y is not in the closure, then this is the case. And if this is the case, then y is not in the closure. That's how this proof's going to go. So 1. So we're proving this direction. 1. Assume y is not in a closure. Okay. If y is not in a closure, then then what does that mean?
There's no neighborhood that includes A.
Well, we're going to prove this, but just what does it mean to not be in a closure? Maybe I'll just say it. It's a bit of a leap to get you to just come up with. So if y isn't in the closure, then it's in the complement of the closure. Right?
Yes.
Okay. Now, a closure is open or closed?
Close.
Closed. So its complement is
Open.
open. So y is inside some open set. And if y is inside so this is an open set.
Wouldn't that mean y is in the interior of A?
No. So let's draw a picture of this to make sure we're on the same page. So we'll go back to here's A, right? Here's a closure. If we take the complement of a closure, then that's all the points that aren't a closure. So that is all the points out here.
If that ball's A. Or is that just some random point outside of A closure?
No, this is redrawn the same This points over and over again. This is a complement of this set. If this is A closure, here's its complement. A closure is all the points inside this ball, including the boundary, right? So its complement is all the points. We basically, I've got the whole plane and I ripped that circle out. What am I left with? I'm left with what we have down here. I'm left with the whole plane with that circle missing. So this down here is A closure's complement. So definitely not the interior of A.
So the interior of A would be like.
So A is these points.
Including ones.
The interior of A, it has a similar picture, but it's all these points.
Just not including the boundary.
Not including the boundary. So here's A interior. Here's A closure's complement. Very different sets. Okay. So let's see. So Y is in A closure's complement, and we know that A closure's complement is open, right?
Yeah.
What am I trying to do? I am trying to find some open set, some neighborhood of Y, such that when you intersect it with A, you get the empty set, right? Now my open set is going to be this thing. So this is going to be my use of Y. Here's an open set that contains Y. Now I just need to show that its intersection with A is the empty set. 2. Since A is a subset of A closure, since A is a subset of the complement, then how's the best way to say this? I don't know if I can go straight to it. Let me say it in words first, and then I'll figure out how to write it. If A is a subset of A complement,
Then A.
everything in here is in here, and I have all of X, and I get rid of the points in A complement, I also got rid of the points in A. So I have all of X here. If I get rid of all of A complement, I rip that out. I also ripped out all of A.
So I mean A closure.
No. Oh, do I keep calling this? Yes, sorry. Thank you. Let's say this again. Everything that's in A is in A closure. If I were to take A closure and rip it out of the whiteboard, I ripped out all of A. Right?
Yeah.
Yeah.
So what I'm getting at is that A intersect A closure's complement is the empty set. They have no points in common. If I got rid of all of A closure, I got rid of all of A. And so when I intersect A with A complement's closure, A closure's complement, we're left with the empty set. You follow the logic there? Or, let me say it another way. Maybe this will be a good piece of logic to throw in there in between. If A is a subset of A closure, then A closure's complement is a subset of A complement. If everything that's in A is in A closure, then everything that's not, I am so sorry guys. This is A closure complement. So this is everything that's not in A closure. So if everything that's in A is in A closure, then everything that's not in A closure is also not in A. So these are all the points that don't have A. This is a subset of that. So this must not have A. This doesn't have A. This is a subset of this. So this can't have A. Because if it did have A, this would have A. You with me? So this can't have any of A in it. So getting back to the same thing I just erased, the whole point there is A closure's complement intersected with A is equal to the empty set. So that was our whole goal. Our whole goal was to show that if y is not in a closure, then we can find some neighborhood of y, here's one, some open set containing y, here's one, where when you take that open set and you intersect it with A, you get the empty set. So 3, if we want to spell it out, let u sub y equal A complements closure, comma, and observe that u sub y intersect A is equal to the empty set. So we found some open set containing y, such that when you intersect with A, you get the empty set. That was our whole goal. So I showed that if this is the case, then this is the case. Now we gotta go the other direction. Okay, so now we're going this way. Now I'm going to show that if we have some open set containing y, and that open set doesn't intersect A, or in other words, when you intersect it with A, you get the empty set, then y must not be in the closure of A. So, next, we'll say assume that there exists some u sub y, some neighborhood of y, such that u sub y intersected with A is equal to the empty set. Okay. Let me scribble some work. I'm not sure how I'm going to do this yet. If I'm trying to show that y is not in A closure, I'm trying to get that y is in A closure's complement. How do I want to do this? Assume that there exists u sub y such that u sub y intersected with A is the empty set. I know u is open, so let's say let v sub y equal u sub y's complement. I know u sub y is open, so v sub y must be closed. So I know v sub y, that gives me v sub y is closed. And I also know that A is a subset of v sub y. How do I know that A is a subset of v sub y?
Because v sub y is a complement of u sub y, and complement of u sub y is, well, y is an area that's outside of
Yeah.
A.
You got the right idea, just struggling with words. U sub y contains none of A.
Yeah.
U sub y intersected with A is the empty set. Whatever u sub y is, it has none of A. V sub y is a complement of u sub y. V sub y is everything that's not u sub y. All of A is for sure not u sub y. V sub y is everything that's not u sub y. Therefore, A has to be a part of v sub y. So v sub y is a closed set containing A. Right? What is A closure? The smallest closed set containing A. V sub y is a closed set that contains A. A closure is the smallest closed set that contains A. So I now know that A closure must be a subset of V sub y. Right?
Yes.
So A closure is a subset of V sub y. 6. Observe that observe that y was in u sub y, right? U sub y is a neighborhood containing y. That's what we meant by u sub y. So if y is in u sub y, is y in v sub y?
No.
No. So that gives me that y is not in v sub y, right?
Yes.
And if I know y isn't in v sub y, what else do I know y isn't in?
A or
A
A
closure.
closure.
A closure. So that gives me that y is not in a closure, which is where we were trying to get. It's trying to show that if there was some neighborhood of y, such as intersection with A is the empty set, then dot 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 y is not in a closure. We did it. That's the big theorem of the day. That's the one we're going to use over and over again. It's sick how many times we're going to use this. Got to get comfortable with it. All right, let's do 4 more, hopefully quick theorems, and then we're done. Mostly they're theorems to help us practice using what we just proved. So, not as important, but just meant to help you practice using what we just did. Oh my goodness. Should I got back up? Okay. Good. All right. So, these next 4 theorems, well, 2 of them, the next 2 theorems that we're going to prove, here's what we're going to, let A and B be subsets of some topological space X. Then we have these 4 properties. Here's what the 4 properties are going to be. The interior of A complement is the complement of the closure of A. In other words, if you pull the complement outside of an interior, it converts it to a closure. Or if you shove the complement inside of a closure, it flips it to an interior. And then this is just the same thing, the converse of that. This is, if you have the closure of a complement and you pull the complement out, it turns your closure to an interior. So, distributing a closure, complement. Distributing a complement into an interior converts it to a closure. And distributing a complement into a closure converts it into an interior. Make sense what the first 2 are?
Yeah.
Okay, so let's prove the first 2. Maybe let's just draw out a picture actually, first of all, to get a feel for these. So, let's start by drawing some arbitrary A. And we'll go back to the A we all know and love. The one that has some points and doesn't have others. Here's our A, right? Now first, so I may come up with this picture, we're going to look at A complement and then look at its interior. So A complement, if we draw that over here, that is going to be all the points here, not here, but now we're on the outside. So now we're talking about the points out here, right? This is A complement. I have to come over here. Okay, now take the interior of that. It's just going to be, we can't include these boundary points. So, A complement's interior, should have spread my hand first. The interior of A complement is going to be that, but all the outside points, not the inside points. Right to me?
Yeah.
Now, let's go through this process. So we start with A. First, we're going to take its closure, then the complement. So A to A closure, what does A closure look like?
Just that same point, but everything.
The circle, but we're talking about the points inside, right?
And the border.
And the border, right. Perfect. And now, take the complement of that. So now we have A closure's complement, and what do we get? We get the whiteboard ripping that out. So we're left with this hole, but we have all the points outside. So all the points outside an open circle, all the points outside an open circle, same thing.
What?
So, taking A, doing the complement in the interior is the same thing as first doing the closure, then the complement. There's a picture for it. Good? Let me get my eraser. maybe we'll reference a picture as we go. So let's begin. So trying to prove that these are equal to each other. The interior of a closure is equal to the closure, or is equal to the complement of the closure of A. Here's the way I'm going to write it. The interior of a closure is equal to the interior of a complement is equal to the complement of a closure. Right? Okay, so let's get started. I'm going to show that this is a subset of this and this is a subset of this. That's the way we show two sets are equal. So let X be a point in the interior of a complement. So interior of a complement, that's over here. We're grabbing some random point inside of it. And I need to show that point is also in here. Okay. So let X be in the interior of a complement. And observe that the interior of a complement is always and forever a subset of a complement. Right? This set is a subset of this set. The interior of a complement is a subset of a complement. Where were we? You're right here. And that's always the case. A set's interior is always a subset of the set. A complement is just a set. Don't be confused that we spelled it with two letters instead of one. Okay. So then, a complement's interior is an open set. And since it's a subset of a complement, then what's its intersection with A?
0.
The empty set. It is a subset of everything that's not A. What's in here? Not A, that's for sure. So when you intersect it with A, you get nothing. So it's an open set. We found an open set containing X. And its intersection with the empty set, or its intersection with A is the empty set. Then by theorem 2.5, X must not be in a closure. How do we know that a set is not in a closure of A, or a point is not in a closure of A, is logically equivalent to there is some neighborhood containing the point where that neighborhood's intersection with A is empty. So we found some neighborhood containing the point, namely the interior of a closure, or of a complement, the interior of a complement. There's an open set containing X. When we intersect it with A, we get the empty set. Therefore, X is not in the closure of A, which is the same thing as X is in a closure's complement. That's what it means for X to not be in the closure of A. It's in its complement. So a bit of logic there, but we just really showed that if X is in a closure's interior, if X is in a complement's interior, then X is in a closure's complement. So far I've showed that this set is a subset of this set, which is what we have right there, right? Now I need to go the other way. I need to grab a point out of here and show that it's in there. So other direction this time. Let X be a point in a closure's complement. Right? Now, if it's in a closure's complement, then it's definitely not in a closure. And by theorem 2.5, if you're not in the closure, then there has to be some open set containing you, such that when I intersect it with A, we get the empty set. So since our point is not in a closure, then by theorem 2.5, there must exist some neighborhood of X, some open set containing X, such that when we intersect it with A, we get the empty set. Or in other words, that U sub X has to be a subset of a complement. If it contains none of A, then it's a subset of the set that's everything that's none of A. This is everything that's none of A. This is something that's none of A. So it's a part of everything that's none of A. Follow that? Okay. So then U sub X is open, and U sub X is a subset of a complement. What is the interior of a complement? It's every open set that's a subset of A complement. U sub x is a subset of A complement that's open. A complement's interior is every open set that's a subset of A complement. And so U sub x has to be a subset of A complement's interior, because it was an open set in A complement. So, since x was in U sub x, then obviously x is in the interior of A complement. Good? So, I showed that one's a subset of the other, and I showed the previous subset somewhere up here, right there. So we have this is a subset of this, we have this is a subset of that, therefore they're equal to each other. Good? Okay, let's do the second one. This time, if we take the complement of A and then its closure, that's the same thing as taking the interior of A and then its complement. So before we showed taking the complement then the interior is the same thing as taking the closure then the complement. Now we're saying taking the complement then the closure is the same thing as taking the interior then the complement. Alright, let's prove it. So, observe that the interior of A is always and forever a subset of A. Right? Mm-hmm. Which means that A complement is a subset of A interior's complement. If I get rid of everything that's in A, it's the same logic we used over here when we did this leap. We said if A was a subset of A closure, then A closure's complement is a subset of A complement. If you complement both sides, it flips your subset symbol. It's kind of like multiplying both sides by a negative number to flip your less than or equal number. If I know that x is less than or equal to y, I know that negative x is greater than or equal to negative y. Similar thing we're doing here. So that's what we're doing from here to here. If I get rid of all of A, everything that's not A's interior is bigger than everything that's not A. What's bigger? A or A interior? A is bigger than A interior. So if I get rid of A, if I want to keep the most points, what should I get rid of? A or A interior? If I want to keep the most points. Get rid of A interior, right? So when we get rid of A interior, we still have more points than if we get rid of all of A. So the complement of A interior is bigger than the complement of A. If we get rid of A interior, we got rid of less points than if we would have gotten rid of all of A. So there's intuitive for it, or maybe it's already obvious to you. You see, oh, we're not doing both sides, or we're doing the negative both sides, and it just flips the subset symbol. That's another way to say it. Whatever works for you. But hopefully something's working for you, and it makes sense. Okay, so I now know that A complement is a subset of A interior's complement. Now, A interior is an open set, so A interior complement is closed. So this is a closed set containing A complement. What is the closure of A complement? It's the smallest closed set containing A complement. Here is A closed set containing A complement. A complement's closure is the smallest closed set containing A complement. So then A interior's complement is a closed set containing A complement. So the closure of A complement has to be a subset of this closed set. This is the closed set containing A complement. This is the closure of A complement. And so it's the smallest closed set containing A complement. So this is less than this. Less than or equal to, right? Okay. So now, we showed one direction of this. We showed that this was a subset of this. Now I need to show that this is a subset of this. That one I need to do the more direct way. I don't have a nice easy trick for it like I did this one. So I'm going to grab a random x out there, show it's also in there. Therefore everything that's in here is in here. So I already showed this is a subset of that. That's what we have written right there. Now I need to show this is a subset of that. How am I going to do that? I'm going to say let x be any random thing in here. I'm going to show it's also in there. So now, let x be anything in the complement of A's interior. Right? And let u sub x be any open set containing x. Question. Is u sub x a subset of this set? So far we have no idea. So we have two things written up here. I have x is in here, and I have that u sub x is any open set containing x. All I know is that these two sets must intersect at least one point, namely x. X is in here, and x is in here. This is any open set containing x, and this is some closed set containing x. It's complement of an open set, so this one's closed. Some closed set containing x, some open set containing x. Okay. Now, since x is not in the interior of A, how do I know that? Well, x is in A interior's complement. So x is not in the interior of A. Then u sub x is not a subset of A's interior. And so it's not a subset of A. How do I know that u sub x is not a subset of A's interior?
Because it's not part of A. No, sorry.
What's the one point I know is in u sub x?
X.
X. What's the one point I know is not in the interior of A?
X.
So is it possible for u sub x to be a subset of the interior of A? No. Because x is in here, and x for sure isn't in here. So whatever these sets are, this definitely is not a subset of that. And so that gives me that u sub x is not a subset of A. How do I know that it's not a subset of A? U sub x is open. If it were a subset of A, it would be part of A's interior. But it can't be part of A's interior. So it can't be a subset of A. If u sub x was a subset of A, then it would be an open set in A. The interior of A is every open set in A. We know that u sub x is not part of A interior, therefore u sub x cannot be a subset of A. So, u sub x intersected with A complement is not empty. Probably should have said this first. Let me say this first. So u sub x intersected with A is equal to, well, no, that's still not right. How I have it here is the next step you have to take. If u sub x is not a subset of A, then u sub x has to have something that's not in A. If u sub x is not a subset of A, u sub x has to have something that's not in A. If everything in u sub x was in A, then u sub x would be a subset of A. But since u sub x is not a subset of A, u sub x has to have something that's not in A. If u sub x has something that's not in A, then u sub x has something that is in A complement. If u sub x has something that's not in A, then u sub x does have something that's in A complement. Right?
Yes.
And so u sub x intersected with A complement can't be empty. If u sub x intersected with A complement was empty, then u sub x would have to be a subset of A. But u sub x isn't a subset of A. It's got something that's not in A. So it's got something that's not in A. So what did we show? We just really showed that for any u sub x you choose, any open set containing x, we knew nothing about that set except for that it was open and contained x. So we showed that for any u sub x you choose, any open set containing x, when you take it and you intersect it with A complement, it's not empty. Therefore, x is in the closure of A complement. We're using this theorem, but now we're using it this way. If you have this, then you have this. I just barely showed that for any open set containing x you find, that open set, when you intersect it with A complement, is not equal to the empty set. Therefore, our point is in a complement. It's the same thing we have written over there. Just replace your u sub i's with t sub x's and replace your a's with a complements. And we prove the exact same thing over here. So writing it out so that you can see one for one what we showed, we just really showed that for all u sub x intersect with a complement is not equal to the empty set. So that implies that x is not in a complement closure. Sorry, I don't know if I can see down there. So notice that this is exactly what we have written over there, just replacing your y's with x's and your a's with a complements. Okay. So those were the two example proofs where we had to use that theorem over and over again. Here's two other proofs for completeness. I don't know that we use that theorem again in proving them. So now, two easy ones. Prove that the interior of A union with the interior of B is a subset of the interior of A union B. Okay? So the interior of A union together with the interior of B is a subset of the interior of A union B. I didn't want to just do a circle above it. I thought that'd be weird notation. So here's where I use an int rather than the open circle above it. Okay, so let's prove that this is the case. Observe that A interior is a subset of A union B. Right? A interior is a subset of A, so it's definitely a subset of A union B. And it's open. A interior is definitely an open set. So A interior is open, and it's a subset of A union B. Therefore, A interior is in the interior of A union B. The interior of A union B is all open sets that are a subset of A union B. This is one of those subsets. Okay, now observe that it's the exact same logic. B interior is a subset of A union B, and B interior is open. So B interior is an open set. So B interior is one of the open sets in the interior of A union B. Exact same logic. Therefore, I showed this set is a subset of that, and this set is a subset of that. So when you union it together, it's still a subset. Everything in here is in here, and everything in here is in here. So when you union them together, you get things in there. Now, you notice that this says that the interior of A union together with the interior of B is a subset of the interior of A union B, not equal to. Turns out when we switch to intersection, it's equal. Here it's not equal. So I'm going to give you a quick counterexample as to why it's not equal. So why not equal? Imagine we're standard topology on R. Open sets are open intervals, A comma B, and then a union of open intervals. Right? Standard topology on R. Let's say that A is equal to this set. What is A interior equal to? We'll write over here, we're going to use space. What is A interior equal to? Standard topology on R. Our open sets are open intervals. What's the biggest open interval I can fit in here?
Parentheses 1.
Parentheses 0.
Just the open interval 1 to 2. Yep.
Yeah.
Just like that. That's the interior of A. Okay. What's the interior of B?
B.
Just B. The open interval 2 to 3. Right?
Yeah.
Now, what is A union B? Not A interior union B interior. A union B.
1, 2, 3.
All the numbers from 1 to 3. It's not just 1, 2, 3. 1.5 is in there. 1.2796417 is in there. All the numbers from 1 to 3, not including 1 and 3, but every possible number in between. All right? What is the interior now of A union B? What's the interior of this?
1, 3.
1, 3. But notice that when we union these two together, what do we get?
1, 3.
1, everything up to 2, then 2. Well, then a little bit.
Everything between 1 and 3 except 2.
Oh.
So when we union these together, we missed 2. Where over here we got 2. So the open interval 1, 2 union together with 2, 3 is just a subset of 1 to 3. So A interior union B interior is just a subset of the interior of A union B. It's not necessarily equal to it. Okay, last one, this one, where it's actually going to be equal to it. So the interior of A intersected with the interior of B, it turns out is the same thing as the interior of A intersect B. Okay, so let's prove that one. So we're going to prove that this is a subset of this, then this is a subset of this. So first let's prove that this is a subset of this. So observe that. So A interior is a open set, right? B interior is a, and if I intersect two open sets together, it's still open. Any intersection of finitely many open sets is still open. 2 is definitely a finite number. So an open set intersected with an open set is still open. So this is an open set. Now, since A interior is a subset of A and B interior is a subset of B, then A interior intersect B interior is a subset of A intersect B. So this is an open set contained in this set. This is an open set contained in this set. Therefore, this open set has to be in the interior of this set. So, this open set is a subset of the interior of this set. Follow that? Now let's go the other way. If I show that this is a subset of this. This one I'm going to do good old-fashioned, grab a random x out there and show it's also in there. So let x be in the interior of A intersect B. Now if x is in the interior of A intersect B, there has to be some open set containing x, some neighborhood of x, such that that open set is a subset of A intersect B. Right? Okay. So, if that open set is a subset of A intersect B, then that open set has to be a subset of A, and it has to be a subset of B. That's the only way for it to be in their intersection. What does it mean for you to be in A intersect B? It means you're in A and you're in B. That's what it means to be in their intersection. So U sub x is in A and U sub x is in B. So U sub x is an open set in A, which means U sub x is in the interior of A. Similarly, U sub x is an open set in B. Therefore, U sub x has to be in the interior of B. So then, x is in both the interior of A and the interior of B. Right? So I just barely showed if it's in the interior of A union or A intersect B, then it's in the interior of A intersected with the interior of B. So I just barely showed this is a subset of this. So I showed the first is a subset of the second is a subset of the first, therefore they're equal. And we're done. And that gets through the section on interiors and closures. And next week we start limits, just like you do in calculus. Any questions you want to record before we turn it off? Tell your friends they better watch it or they're in trouble. Because without this lecture, no chance on limits.